Welcome back, Chemistry 30. This is the section EC1.4, Electrochemical cells. So looking at oxidation reduction as it pertains to cells. Illustrate and label the parts of an electrochemical cell and explain how it works, including half reactions, flow of ions, and flow of electrons. So the energy released in a spontaneous redox reaction can be used to perform electrical work. This task is accomplished through the use of an electrochemical, or sometimes referred to as voltaic or galvanic cell, which is a device in which the transfer of electrons takes place through an external pathway rather than between the reactants present in some vessel. So an external wire that's connected. One such spontaneous reaction occurs when a strip of zinc is placed in contact with a solution containing Cu2+ ion. So it could be a solution of copper sulfate or copper 2 nitrate, in which, of course, in solution, in aqueous solution, these are broken down into Cu2+ and SO4 negative, or Cu2+ and NO3 negative. So you have solid zinc, and you have the copper solution, right, that has the copper ions. The copper sulfate solution is a blue color. Now, as the reaction proceeds, the blue color that contains the copper ions and whatever anion it is, whether it's sulfate or nitrate, begins to fade, and copper begins to deposit on the zinc. At the same time, this zinc appears to dissolve. So if you take a look at the schematic here, we have the zinc strip here, the copper solution. And if you look here, so if these closely packed atoms represent the zinc metal, okay, and we have the copper ions floating around in solution, what happens here is that the zinc tends to lose electrons, and those electrons get taken in by the Cu2+ ions to become Cu atoms and attach themselves here. And the zinc atom, when it loses electrons, it becomes Zn2+. It becomes the ion in solution. So the solution is changing its identity from what was originally copper 2 becomes zinc 2. So kind of switching places there. So the solid zinc combines with the copper ions. Zinc gives its zinc gives its electrons to the copper ions. The zinc then becomes the solid, or copper becomes the solid, and zinc turns into ion form. So that's what's happening here. And you can see here in this picture, even though it's not clear, you can see a deposit here of copper. So the transformations are summarized below here. So the zinc solid and the copper 2 ions, there's electron transfer. Then we have the formation of zinc ions and copper solid. The figure on the right shows a voltaic cell that uses redox reactions given in the above equation. Although the setup in the figure is more complex, the figure on the previous page, the reaction is the same. The significant difference is that in the voltaic cell, so it has an external wire connected here. In the voltaic cell, the zinc metal and the copper ions are not in direct contact with each other, such as on the previous page. Instead, the zinc metal is in contact with zinc ions in the solution, so it could be zinc, so it's zinc sulfate here with zinc. And the copper metal is in contact with, it's in just the copper sulfate solution. Okay, so we have a copper and copper solution, zinc and zinc solution. And consequently, reduction can occur only by the flow of electrons through the external circuit. So here we have this voltmeter connected. So electrons run from one wire into here and into the other one. Electrons flow through the wire and ions move in solution. Both constitute an electric current. This flow of electric charge can be accomplished to do electrical work. The two solid metals that are connected by the external circuit are called the electrodes. So that solid zinc and the solid copper, they are referred to as electrodes. By definition, the electrode at which oxidation occurs is called the anode. So you can think of it as loss of electrons, anode. So maybe a name, Leo anode. And the electrode at which reduction occurs is the cathode. So GR cathode. You can think of it as cats say GR as well. GR cathode, LEO anode. The electrodes can be made of materials that participate in the reaction, such as seen in this example. Over the course of the reaction, the zinc electrode will gradually disappear and the copper electrode will gain mass. Because remember, the zinc atoms are continuously breaking apart and turning into zinc ions, and the copper ions are taking in electrons and becoming copper, solid copper. More typically, to avoid the breaking down of electrodes are made of conducting material such as platinum and graphite that do not gain or lose mass during the reaction. So they can add electrons or take away electrons, but they won't degrade themselves. Each of the two compartments of a voltaic cell is going to be a half cell. So at the anode area, where electrons are lost by the anode, that's where the zinc solid is breaking down into zinc ions floating around in solution and giving up electrons. And at the cathode, we have the copper ions receiving electrons and depositing on the strip there. So we have that happening. So one half cell is the oxidation half and the other side is the reduction. So this is what we have happening here. So the zinc, that's happening, and the copper, it's gaining 2 electrons. Electrons become available as zinc metal is oxidized at the anode. They flow through the external circuit to the cathode, where they are consumed as Cu2 plus ions are reduced. Because zinc is oxidized in the cell, the zinc electrode loses mass, and the concentration of zinc ions increases as the cell operates. So in the beaker that has zinc, the zinc solution, we're going to get these increasing. Similarly, the copper electrode gains mass, and the copper 2 solution becomes less concentrated as Cu2 is left, and it's reduced to copper, solid. For a voltaic cell to work, the solutions in the 2 half cells must remain electrically neutral. So, because there's a problem happening here, right? You have zinc ions entering this solution here. You have copper ions exiting this solution here. So there's going to be a problem inside here. As zinc is oxidized in the anode department, so thus there must be some means for positive ions to migrate out of the anode compartment and negative ions to migrate in to keep the solution electrically neutral. Similarly, the reduction of copper too at the cathode removes positive charge from the solution leaving an excess of negatives. Thus, we must have a way to have positives enter in there to in fact make it electrically neutral. In fact, no measurable electron flow will occur between electrodes unless we can neutralize those solutions. So in the figure on the previous page, a porous glass disc was used. So if you look over here very carefully, there is a little area there in which the 2 solutions could mix. Over here, though, another way you could do it is by using a salt bridge. So in the figure below, a salt bridge serves that purpose. So it could be sodium chloride, for example, that have sodium ions and chloride ions. So over here, when we have zinc breaking down to make Zn2 plus ions, we would have way too many. So originally this is a zinc nitrate solution in this example, okay, zinc nitrate. So but if we get more zinc ions here, eventually we run out of nitrates to neutralize that. So the Cl minus ions from the salt bridge can enter and then balance out the extra positives that are in here. Over here, we have a zinc or a copper 2 nitrate solution. So as copper ions leave to make solid copper, we're of course losing positive ions. So we need a way to have more positives added in here to neutralize the negative nitrates, and that's where sodium enters the picture here. So whatever we need here for ions is accomplished by the salt bridge. So we have the zinc becoming oxidized, becoming zinc 2 plus ions entering solution, And when the electrons are lost, so this plate here, this zinc anode, begins to accumulate electrons, which of course lose electrons. And then over here, we have the electrons being taken up by the copper 2+ ions, and they become copper atoms, which deposit onto here. And if you look over here, this is eventually what happens. The zinc anode, since it's losing solid zinc into zinc ion form, it begins to, well, lose zinc. And over here at the copper cathode, we get more deposits of copper. So the cathode actually becomes more massive, whereas the zinc becomes less massive. All right, I think we'll stop it there, and then we'll continue this discussion in the next video.